Welcome to another new video of interesting math problem on our channel Math Solutions for You. Please do like, share, comment, and don't forget to subscribe to our channel. We are given a figure ABCD, and by the look of it, it is a quadrilateral, but this is not the regular quadrilateral shape that we are most commonly used to. So this shape, it's an arrow shape, it's called a concave quadrilateral. And we are given some dimensions, namely AB is equal to 2, AD is equal to 2, and some of the included angles, namely angle BAD is 60 degrees, then angle ABC is equal to angle ADC equal to 15 degrees. And we are asked to find the area of this concave quadrilateral ABCD. Now this concave quadrilateral, the shape is unfamiliar, and there is no formula that's easily known that you can apply to either the angles or the dimensions to come up with an area. And whenever you encounter a geometric shape that's not as familiar, the way to go about the problem is to somehow, express the area of the figure that you are given in terms of some simple algebraic addition or subtraction of areas of known shapes. And in this case, it's actually pretty obvious. So if you want a known shape, if you join BD, then you get this triangle ABD, right? And you can find the area of the quadrilateral ABCD or the shape ABCD by subtracting the area of the triangle BCD, which is a smaller triangle, from the bigger triangle, triangle ABD. Now let's focus our attention to the bigger triangle ABD that's formed as a result of this construction. And in this triangle ABD, AB is equal to AD. So that's given, right? Both of those sides are equal to 2. So that makes triangle ABD an isosceles triangle because two of its sides are equal. And what's more interesting and convenient in this case is the angle included between those two equal sides, AB and AD, in triangle ABD is 60 degrees. And whenever that's the case, when a triangle is isosceles and the angle included between the two equal sides is 60 degrees, we know that the triangle is not only isosceles but it's also equilateral, meaning that the other two angles would also have to be 60 degrees each. So those are the two angles marked in blue, namely triangle ABD and triangle ADB. So each of those angles will have to be also 60 degrees. And that will make this whole triangle ABD an equilateral triangle. So BD will be also equal to AB and AD, and hence it will be equal to 2. So next, focus our attention on the smaller triangle, namely triangle BCD. Well, we have found that angle ABD, that's the angle marked in blue, is 60 degrees. And then we are given the smaller angle, angle ABC, that's 15 degrees. So, and that's pretty much true on either side of this triangle, right? So what does that make this angle marked in green, angle CBD, and on the other side, angle CDB? We know that they should be both equal, but what is their value? Well, we have the entire blue angle, 60 degrees, and then the green angle plus 15 degrees should be equal to the entire blue angle. So whatever the green angle is, plus 15 degrees should equal 60 degrees. So we can find the green angle by simply subtracting 15 degrees from 60 degrees. So that gives us each of those green angles marked in the figure as 45 degrees. Now in triangle BCD, we have two angles that are equal and each are 45 degrees. So that makes triangle BCD an isosceles triangle. But then again, it's not just any isosceles triangle. It's an isosceles triangle where two of its equal angles are 45 degrees. And that makes the other angle, namely angle BCD, equal to 90 degrees. So triangle BCD is a special kind of isosceles triangle. So it's a right-angled isosceles triangle, right? Where we have the angles as 90, 45, and 45. So that will basically make the lengths of the sides BC and CD equal. So let that length be x. Now, triangle BCD is not only isosceles, but it's also right-angled. So we can apply Pythagoras Theorem. The hypotenuse is BD, and the two legs of the right-angled triangle BCD are each equal to x. So if you apply Pythagoras Theorem, we can write this: x square plus x square is equal to 2 square. So 2 being the hypotenuse, so the sum of the squares of the two legs of the right angle is equal to the square of the hypotenuse. So that's Pythagoras Theorem. And from this, we obtain 2x square is equal to 4, from which we have x square is equal to 2. So what's the area of triangle BCD? Well, the area of triangle BCD, the BCD being a right-angled triangle, its base can be regarded as BC and altitude can be regarded as CD. So it's simply half base multiplied by altitude, so half BC multiplied by CD. And again, each are equal to x, so it's simply half x square. And we know x square is equal to 2, so we substitute that, and this becomes half multiplied by 2 equal to 1. So area of triangle BCD turns out to be 1. Now, what about the area of the triangle ABD? We know that it's an equilateral triangle. And for an equilateral triangle, its area is given by root 3 by 4 multiplied by square of the side. And in this case, each side of the equilateral triangle is 2. So we have the area as root 3 by 4 multiplied by 2 square, which simply comes to root 3. So now we know the areas of these two triangles. We can easily find the area of the shape ABCD as the difference of the areas of triangle ABD and triangle BCD. And that comes to root 3 minus 1. So the correct option in this case will be option B, root 3 minus 1.